first of all, my name is Jeff. I work at Nimiq, which is a blockchain project, a web-based blockchain project. This is based off of a workshop that is an 8 hours long workshop. And I had to basically cut it off for this specific 30-minute talk, so I hope we can get most of it. Okay, well, this is a little bit about the history of blockchains. I just don't work on this PDF. Okay, basically, there are some technologies that were initially used trying to solve the idea of having, digital cash, and well, some other problems like spamming the internet. Eventually, someone by the name of Satoshi Nakamoto, we don't know who that persons, aliens, or whatever it is, really is, posted a white paper that described how to solve the last problem we had with real digital money, which was the double spending problem by using Nakamoto consensus. And eventually that led to some people, most notably Vitalik Buterin, trying to increase or improve this concept so that they could have, or we could have, a universally programmable machine that was run in a decentralized fashion. And then there have been several versions of this. It was called Ethereum, the project. The last one is supposed to be released, like a couple of weeks ago. There was a small technical glitch for those who know about it. And well, now we hopefully it will be released like at the end of February. Okay, there are some basic concepts of cryptography that one needs to grasp if one wants to understand this. Because you're at the blockchain event, so I'm going to assume that most of you know about asymmetric cryptography, at least how it works, not of course the theoretical parts of it. If someone doesn't know, then ask me during the party, and we can talk about it a little bit. I'm assuming you guys know about what a peer-to-peer network is. And then we're going to get directly to the Ethereum part of this stuff. To understand how programming Ethereum works, you actually need to understand first what you are programming. So Ethereum is basically based off of a virtual machine, in the Java virtual machine sense, not in the VMware virtual machine sense. And the idea is that you're actually, when you are programming, you are actually creating high-level code that eventually will be compiled into bytecode of this specific machine. And you need to understand that in order to create correct programs. Hopefully someday we will have some better tools that will maybe allow us to, abstract that the way we kind of abstract today how a real, CPU works, and we can still program it. But for now, there have been a lot of mistakes. Leo here is going to talk us about it later, that people have made because they don't understand how this machine works. So I think it's still important to understand it. Basically, the Ethereum virtual machine is an execution environment that runs in every Ethereum node. Every person that is running a full node for Ethereum has this virtual machine as part of their node. It's completely isolated. That is something very important to understand. Basically, it means, because of course, right, if I have strangers uploading code to my computer, I don't want them to be able to access my files or my network directly or my memory. So it's basically an isolated part of this node. With no access to any of the real physical resources on the computer that the node is running. This virtual machine also has accounts, has basically two types of accounts. External accounts, which are meant to be used by humans. So these are what you usually think of as accounts when you are using Ethereum to send Ether to another person. That's usually an external account. What it also has, and this is the main difference, I guess, with Bitcoin or other cash blockchains, they also have accounts that are meant to hold code, and they are not controlled by a human, but controlled by the code that defines that account. Accounts, we will see later how that works, but accounts also have a storage space, and they have a balance. So the balance is the amount of Ether. Ether is Ethereum's currency. It's the amount of Ether that the account holds. There's also transactions in the Ethereum virtual machine, and transactions are basically messages between accounts. The message can have an amount, such that it can move money from one account into another, but it also can have a payload, and the payload is just data that will be passed to in the transaction to the account. if the account, the destination account we're using is actually a contract, a smart contract, then when you send a message to that account or that address, what will happen is that the code will be executed and this payload will be used as input data for that specific contract. And then there is a special case when the account destination is null or otherwise undefined, then that's how you create new contracts into the Ethereum virtual machine. The Ethereum virtual machine also has a very important component called gas. The idea of gas is basically that, every time you're executing something in the Ethereum virtual machine, you're actually using resources of a lot of people. So you should pay for those resources, and gas is the way you do that. It's also important because it prevents a lot of, it prevents attacks. For example, the most obvious attack is that I could create a code that will go something like while true, and then of course I will have the whole computer for everybody. You don't want that to be possible, so gas prevents that, because when you start executing code like that, eventually the gas will run out and the execution will stop. It's supposed to be decoupled from the price of Ethereum, because the price of Ethereum has gone up a lot since it started. The idea is that gas shouldn't go up, because then nobody can use the Ethereum computer, because it's actually too expensive to use. And that's done by having two different variables, gas price and gas limit. And then you say that the gas price is the amount you can pay to use the gas, and gas limit is how much gas you will allow to be used in your transaction. The Ethereum virtual machine also has a storage. It's basically a key value store. It's 256 bits wide, both the value and the key. And storing stuff also has a cost measured in gas. There's also basically something like memory, which is started from scratch at the time you send a new transaction to a contract. There's calls, so that you can actually call a contract from another contract. And there's also delegate calls that allow you stuff like shared libraries, because a delegate call will allow you to use the code from another contract in your execution environment. So you can use your storage basically your environment. We also have some logging facilities. They are meant not for the smart contracts to access them, but actually to signal events to the outside world. We'll see a little bit more of that later. The idea is that they are very efficient to look for this, whatever is logged in here, and also can be cryptographically proof, so that it can be used on light clients. You can create, smart contracts can create another smart contract. That's one of the things you can do. They can also self-destruct, so that you have a contract that is supposed to run for a limited period of time, and after that you're completely sure you will never use it again. So you can actually program the functionality so that it will self-destruct. This sometimes is dangerous, because after you self-destruct a contract, if somebody else sends Ether or money to that contract's address, that money is lost forever. So sometimes it's preferable to actually have some kind of deactivate functionality, where your contract will no longer accept any calls, and will just return the Ether back to whatever sender is calling it. Okay, that's basically the architecture of the virtual machine. Solidity is probably the most popular language we have for high-level programming of the Ethereum virtual machine. There are several others attempts. I think there was one called Viper and LLL. This proved to be the most popular one. I think they're also developing a new one. Actually, one of those, Viper, I think, was kind of badly broken. Lido's company did the audit on that compiler, and they found out about it like 2 years ago. So basically, Solidity, if you're going to program smart contracts, Solidity is our best choice right now. Some of its features, it's a high-level language, as I said before. It's contract-oriented, in the same sense as we use object-oriented programming. In this case, it's contract-oriented programming. A contract is kind of like an object in this analogy. That the syntax is similar to JavaScript, but just similar, right? It's not the same as JavaScript, of course. One key difference is statically typed, so every variable has a type in it. It supports inheritance, so you can inherit from other contracts. It supports shared libraries, as we said before, and you can create your own types, and we will see that later on. So basically, this is how the structure of a very, very simple contract in Solidity. This is how it looks. The first line is a pragma. Pragma is, as in any other compiler, a pragma is basically a compiler directive, something you're telling the compiler and it's not part of the compiled code in the end. Here, this contract is very, very simple. What you're doing is, as the name suggests, you're storing some data. So you basically have one variable, store data, that's a state variable, and that will be stored in this contract's storage space. And then you have a setter, a function that will take a variable x of the type uint, which for those of you who have worked at low-level programming, that's an unsigned integer. Integers by default, if they are not specified in Solidity, are 256 bits wide. So you're basically setting this variable to whatever x parameter you're passing to the set function, and then you can use the get function to return that value again. This is of course not a very useful contract because anybody can change it, as you can see from the public there in the set function. But this is probably one of the simpler contracts you can create, and it demonstrates a little bit of how Solidity looks like. Okay, well, state variables in Solidity is basically what I showed you before. Basically, you can store whatever you need to store. This is a store between different calls to your contract. So this is actually information that will remain there. They, as we said before, have a defined type. You have all of the types you will expect, like boolean, integers, both signed and unsigned. You can also have fixed point numbers. That's also a little bit different against other languages. We usually use floating point numbers. And then some interesting things that you wouldn't expect maybe on this. You can have arrays, you can have mappings, and there is a specific type called address type, which is still a 256-bit number, but the compiler interprets it correctly. So, for example, operations like trying to add two different addresses don't make sense, and the compiler will warn you about it. Well, there's of course functions. Functions, as in any other language, they define the code that will be executed. They accept parameters and return variables. They have defined visibility. So there's basically 4 types of visibility: external, public, internal, and private. External visibility is defining that this function is meant to be used by an external entity. It can be a person through an external account, or it can be another contract. It's not supposed to be called from the contract. You can still do it, but theoretically it's not what it's supposed to be. Public is a function that is supposed to be used by anyone. It can be the same contract or an external contract or an external person. Internal is a function that is supposed to be only by this contract from other functions of this contract and from contracts that inherit from this contract. And then private, finally, is supposed to be only used by this contract, not even contracts that inherit from it. Then we have function modifiers. For those of you who have programmed in Python, they are kind of similar to decorators. The idea is that sometimes you need to use exactly the same code in a lot of functions. So you can basically decorate them, or in this case modify them. This example over here, you can see what's going on. I need to make sure that only the seller can call this function. So I basically have in the modifier called onlySeller, I have code that will require that the person calling this function is the seller, has the seller address. Otherwise, I will basically, the require keyword will abort execution, revert the state of the whole machine, and return any ether that was sent to it. And then I can apply this to this specific function abort over here, but I can also apply it to a bunch of different functions. And then if I need to, improve or somehow change this modifier, I only need to change it once instead of changing it in all of the functions that needed this specific functionality. Events are the way that we use the logging facilities of the Ethereum virtual machine from Solidity. So basically you can declare events, like I'm doing over here. The events can take also parameters with their specific types. In this case, we're taking the bidder and amount parameters. Bidder is an address, and amount is an unsigned integer. And then at some point in my code, I can emit that specific event. with the specific parameters set. This is mostly for interfacing with external things, because other contracts and this contract cannot see this. But this will make it easy to log it and like search for these events, filter for these events. Especially if I have some kind of decentralized application, I will probably want to be listening to these events so that I can do stuff with them. And then we have structs. Any of you who have already worked with C, C++, you can probably know about this. Structs are a way to create custom data types, and you do that by basically grouping different variables into one thing that makes sense. In this case, for example, a ballot. In this contract ballot, we have a voter, and a voter is someone that is defined by a weight, by the fact if they already voted or not, by the fact that they can delegate their vote to some other address, and of course by the value of their vote. All of these 4 parameters or 4 variables make sense as one unit, as a voter, so we can do that also in Solidity. And we also have enums. So again, whoever has already programmed in low-level languages is probably familiar with this. Enum permits to generate a set of defined constant values. And in this case, for example, it's very useful when you're defining state stuff. So here you can define the state of a contract being purchased, and then you can have 3 different states: create, locked, or inactive. But again, you can use it for any kind of sets where the values are finite and non and constant. Finally, if you want to start working with Solidity and smart contracts, you probably need more than just, of course, this theory. You will also need tools. There are several tools available that are really useful for this. I will recommend to start with Remix. Remix is actually web-based, so you can just go to this address over here, remix.ethereum.org, and you will get like a complete IDE where you can program Solidity, you can compile it, you can actually even run it, so it has a little bit of emulation functionality, and you can run it step by step, debug it in there, stuff like that. If you are ready to do something a little bit more advanced, maybe you can then start simulating in your own machine. So there's a software called Ganache. The idea with Ganache is that you can run a simulator of the Ethereum virtual machine in your own computer, because usually if you want to program in the real Ethereum virtual machine, you actually need to pay for that, right? You need to pay gas, and most people don't want to try and debug and do all of that directly in the blockchain first. It's also a little bit slow because you need to wait until the blocks are mined, stuff like that. So this allows you to bypass all of that and have like your own Ethereum virtual machine in your computer. You can use that directly. And then there is a framework called Truffle, which I found really useful when I was working on this. It allows you to automate the deployment process to your own Ganache simulator or some test network you created, the real test network, the public test networks out there, and eventually to the public real network or main network of Ethereum. It also gives you a framework for testing, which of course is very, very important in this kind of development environments, because usually when you're working on this, you're working with assets, sometimes money, a lot of it. There are a lot of stories that I could tell you about the problems with that, but Leo is going to handle that. So testing is of course very, very important. When the last contract we did in like the real Ethereum that we deployed to the Ethereum mainnet, I remember it was less than 100 lines of code, and we had like, I don't remember, like 60 or 70 tests for that, because it was handling money, and it was really, really important that it was really fair. And then Truffle also makes it easier to connect with Web3.js, which is basically a library that allows you to connect to the Ethereum network through a proxy node from a web browser. Okay, basically that's it. Okay. So we have about 10 minutes if somebody has some questions. Of course, it's very difficult to actually teach you programming, especially for a new kind of architecture in 30 minutes, but hopefully this is a very good start. I don't know if you have any.
Why don't you tell us about the crowd crowdfunding that you did for Nimiq with Ethereum? Why don't you tell us about the crowdfunding you did for Nimiq using Ethereum and tokens?
Okay. Well, we used this a year and 2 years ago, basically for a crowdfunding event. The idea was that everybody who will send us Ether will get basically a token in the Ethereum network, and then that token can be redeemed for real coins of our network. And that's the first time we were, or I was in contact with this. That's the one contract I told you. It was basically one contract that imported like 2 or 3 more contracts, and in total it was only like 100 lines of code. But we had to do a lot of testing because just at that same time there were several important news about people losing their money. Not only because, well, maybe some of you know about the DAO, and probably maybe Leo is going to talk about that. But the DAO was one of the first or most ambitious projects on the public Ethereum network. It was supposed to be a decentralized organization where people will put money in it and then vote to fund other projects. And someone very famously found a bug in that contract, and then they were allowed to take, I don't remember how much money, I think it was like $80 million out of that. There's also there was another example at that time where one of the exchanges at the time had a bug in their contract, and then nobody took their money. In this case it was even worse, because the money was there, but they could not take the money. The money was stored in the contract, but because of the bug it was impossible to take it out of it. So the money, as far as I know, is still stuck there. It was like $60 million at the time, and nobody can access it. It's in there. So yeah, testing was really important for us. We took a long time and developed that, and make sure that everything was working correctly. This crowdfunding campaign was supposed to last for like, I think, a month. We got to our limit, or the maximum we wanted, in like 2 weeks, but in those 2 weeks it was very difficult for me to sleep and for other people who were involved in this as well. Any other question? Yeah.
No worry about it.
Alright.
Can you tell us a bit about the wallets that you use for testing and also in production? And does Nimiq have a wallet on its own, like a custom-built wallet, or do you use something like Parity or MetaMask?
Okay, yeah, good question. Well, about testing, we use Truffle, and we did our test in JavaScript. With Truffle, you can either do your tests with JavaScript or Solidity, because our blockchain is actually a web-based blockchain, so we're more comfortable with JavaScript. We use that for testing. We actually, and the question about the wallet, well, we are our own blockchain. So we only did this because we needed funding to be able to actually finish our blockchain and then use that. So we have our own wallet because we cannot use any other wallet. We are completely independent of Ethereum now. We only use Ethereum as the beginning phase because we needed the money to fund the project. So initially, for this crowdfunding campaign, people will use whatever wallet they have, MetaMask or my Ether wallet or any of those. But then, right now, we already launched our mainnet and we're completely separate, and then we have a wallet that you can use, and also a little bit of advertisement, I guess. We also support Ledger and hardware wallets and stuff like that, so that people can actually store their funds securely. Any other question?
Tal vez sí nos puede hablar de las diferencias entre estos tipos de contratos, porque yo sé que hay algunos que son ERC20, ERC24, entonces como para tratar de entender bien cuál es la diferencia entre esos tipos de contratos.
Okay, the question is that what's the difference between different kind of contracts, because Esteban has heard about ERC20 and some other terminology like that. Well, basically there are the Solidity, and in general the EVM, it's a machine capable of running any kind of code, right? It's a Turing complete machine, and Solidity is a Turing complete language. So just as in any other kind of architecture that has this, conventions needs to be reached, right? So if I want my contract to talk to your contract, we need to define an interface. So we need to define like which functions we're going to use and what parameters those functions expect and stuff like that. So ERC20 was the first of such definitions for tokens. So basically, it's a definition, a very basic definition of what a token should be and how to interact with it. So it defines, for example, in ERC20 you have a function that allows you to move, right, to send tokens from one person to another, a function that allows you to query the balance for a given address, a function that allows you to let other person move funds on your behalf up to a certain limit. So this interface, they don't define how it should be done in code, but they define the definitions of the functions and the variables. That's ERC20. So after that, people have built, like better ways of doing it, and different kind of tokens definition. Because, for example, ERC20, they are what are known as fungible assets. Like each token is supposedly the same as any other token. There's no difference between two of them. But ERC 721, for example, defines non-fungible assets. So my token is not necessarily the same as your token. One example of that is CryptoKitties, which is very famous, right? So in this case, it's not the same to send two tokens, right? Two of my tokens may not be the same as two of your tokens because they may have a different value or different properties. So that's basically what ERC20 and all of the other different standards are. Any other questions?
Okay, so thanks a lot, Jeff.